When Japan introduced the Mogami-class frigates to the world in 2022, it embodied a shift in naval design philosophy towards reduced manpower requirements, not just in Japan, but in the West more generally. The Japanese Navy is moving away from conventional warships requiring a large crew size, and towards warships with greater automation and reduced personnel requirements. The Mogami-class frigates exemplifies this new paradigm. It is not the biggest ship in the water, nor the most heavily armed, but it possesses a combination of technologies that together make it one of the most versatile frigates in the world. Japan's decision to build the Mogami class emerged from a clear set of strategic requirements. In the late 2010s, the Japan Maritime Self-Defense Force, or the JMSDF, needed a ship that could replace the aging Asagiri-class destroyers and Abukuma-class destroyer escorts. Vessels designed in a different era with little automation, old sensors, and modest offensive and weak defensive capabilities. Yet, the JMSDF also needed to expand its fleet while keeping life cycle cost manageable and crew numbers down, reflecting the increasing scarcity of military manpower. The result was a vessel roughly 132 meters long, displacing about 5,500 tons at full load, with a maximum speed of over 30 knots. The Mogami is, first and foremost, an anti-submarine warfare frigate designed to track, hunt, and deter hostile submarines across Japan's vast maritime approaches. Its core purpose is an escort and patrol platform, protecting sea lines of communication and high-value shipping from submarines, particularly in the complex acoustic environments of coastal waters. The Mogami also carries a credible secondary combat role above the surface. All variants are equipped with cruise missiles for anti-ship warfare, allowing them to threaten surface combatants, while the upgraded Mogami variants adds a meaningful medium-range air defense capability. Beyond these traditional combat roles, the class is designed for unmanned warfare. Its tertiary functions include deploying and controlling unmanned surface and underwater vehicles, extending its reach well beyond the ship's immediate vicinity. It also supports mine warfare tasks from mine laying to mine sweeping, making the Mogami not just a hunter of submarines, but a flexible multi-mission platform. Like any modern warship, the Mogami class cannot be understood in terms of individual systems. It is a ship built around the effective integration of key technologies, many of which are adapting to the emerging realities of naval warfare. 5 key technologies on the Mogami stand out as the most impactful. We'll go over these in the remainder of this video, and the reasons why they make the Mogami class well equipped for future naval warfare. The most impactful of these technologies, and arguably the defining feature of the ship's look, is the integrated radar mast. On warships of previous generations, radar arrays, communication antennas, and electronic warfare sensors were mounted separately on open platforms, often stacked awkwardly up the mast. That architecture created 3 major problems: a large radar cross-section, heavy top weight, and constant electromagnetic interference between systems that were never designed to operate so close together. The Mogami class replaces this with a fully enclosed, multi-function, integrated mast that acts as both a stealth structure and a sensor fusion hub. Inside this mast, the antennas are integrated meticulously to form a compatible electromagnetic ecosystem. The OPY-2 X-band Active Electronically Scanned Array, or ASAR radar, is embedded into the mast faces, alongside passive electronic support measures, identification, friend or foe systems, data links, and satellite communications. The technical challenge here is extreme. Every one of these systems operates on different frequencies, power levels, and cycles. If poorly managed, they can interfere with, desensitize, or even blind each other through signal disruptions. On older ships, this was managed crudely by physical separation. On Mogami, separation is no longer possible if the ship is to maintain stealth. So the solution is deep electromagnetic compatibility engineering. That means careful shielding, precise antenna placement, frequency management, timing control, and software-defined coordination between sensors. Transmit schedules are deconflicted, so high-power radar bursts do not saturate sensitive electronic support measures. The mast itself is built from composite material that allows friendly emissions to pass while absorbing or deflecting the radiation from opposing transmitters. The result is not just stealth, but sensor coherence. ASAR radar technology in the OPY-2 X-band radar amplifies this advantage. Instead of mechanically rotating, the OPY-2 radar steers its beams electronically, allowing it to scan, track, and update many targets simultaneously, while also supporting fire control and electronic protection functions. It can change frequency, waveform, and power on the fly, making it harder to jam or deceive. This means the Mogami can track targets faster and react sooner. The integrated mast is vital because it allows the Mogami class to combine stealth with high-end sensing and electronic warfare. By enclosing radar arrays, communication devices, and electronic support systems inside a single structure, the ship dramatically reduces its radar cross-section while still carrying a full suite of modern sensors. That is why the single structure is arguably the most transformative technology on the Mogami. Secondly, the Mogami class stands out for its deployment of unmanned naval platforms, an increasingly important element of modern network-centric warfare between two opposing systems of systems. The Mogami is designed with an internal mission bay and stern ramp beneath the helicopter deck that can launch and recover unmanned surface vehicles, or USVs, and unmanned underwater vehicles, or UUVs. These unmanned vessels extend the ship's sensor and operational reach far beyond what can be achieved by crewed platforms alone. For anti-submarine and mine countermeasure roles, two missions central to the JMSDF's strategic needs, unmanned systems allow dangerous tasks to be conducted without exposing crew to risk. A UUV, for example, can deploy sonar systems or mine detection sensors in coastal waters that would be risky for a manned ship to enter, and can operate for a long time, feeding data back to the ship's combat system. USVs can undertake patrols or even act as a picket, effectively extending the horizon at which the Mogami can identify and prepare for threats. The much greater capacity to take risk is what makes unmanned naval platforms transformational, and even more so when they are working alongside the more valuable manned warship. Underpinning both the strategic reach and tactical mobility of the Mogami class is its CODAG propulsion system, the first of its kind installed on any JMSDF ship. CODAG, which stands for Combined Diesel and Gas, pairs the efficiency of diesel engines with the high power output of a gas turbine. In the Mogami's case, this means two diesel engines for economical long-range cruising, and a Rolls-Royce MT-30 marine gas turbine for burst of high speed. together producing around 70,000 horsepower. This configuration delivers both a long operational range and tactical agility when it matters. The ship can patrol at moderate speed for long voyages, conserving fuel and reducing operational cost. Diesel engines are more economical during patrol or transit, increasing time on station, a crucial factor for a navy tasked with defending an island nation the size of Japan. However, when a crisis arises, the Mogami can sprint above 30 knots to respond, for example closing with a contact, responding to a threat, repositioning rapidly, or joining up with other naval forces. Cold-deck propulsion is what offers this flexible combination of fuel efficiency and raw power for the Mogami class. Third, no modern frigate can be credible without effective air defense capabilities. While the baseline Mogami class entered service with limited air defense capabilities, the introduction of the Type 23 surface-to-air missile on the upgraded Mogami class significantly enhances its defensive capability. The class was originally fitted with 16 Mark 41 Vertical Launch System, or VLS, cells, sufficient for a mix of anti-submarine rockets and limited self-defense anti-air missiles. But the upgraded Mogami variant is designed with 32 cells, doubling the ship's capacity to carry air defense and other missiles. This expansion is not merely numerical. A larger VLS capacity enables the ship to carry a more diverse weapon loadout, including the Type 23 SAM, a domestically developed ship-to-air missile comparable to the SM-2 family used by many Western navies. While the original Mogami class emphasizes anti-submarine weaponry and has only basic points defense systems like the CRAM for close-in threat, the addition of the Type 23 SAM changes the picture drastically. It allows the frigate to contribute meaningfully to fleet air defense, offering both area protection and self-preservation capabilities. In an era where sea control is closely tied to air defense, the additional VLS and the Type 23 SAM shift the Mogami from a specialized escort to a more well-rounded surface combatant capable of contributing to area air defense. Equally important, although often less visible to casual observers, is the ship's high level of automation. With a crew of around 90, a fraction of what ships of similar size traditionally required, the Mogami demonstrates just how far naval automation has progressed. This reduction in manpower is not about cutting corners. It's about adapting to demographic and budgetary constraints that are inevitably shaping Western naval forces. Japan faces pressures from low birth rates and the rising cost of personnel. By centralizing navigation, combat information, propulsion, and engineering control into an advanced integrated combat information center, the Mogami puts decision-making, system monitoring, and tactical control into fewer hands without sacrificing capability. Automated diagnostics allow a small crew to monitor for problems effectively. If done right, automation can also improve reliability and reduce the risk of mistakes. Because robots and machines don't get tired the way humans do, and therefore don't make the same type of mistakes humans make when fatigued. The net effect is a ship that can stay at sea longer, operate with a smaller crew, and be just as effective and potentially more effective than a less automated ship with a larger crew, a key advantage for navies balancing capability with sustainability. Taken together, these 5 technologies, the integrated radar mast, the integration of unmanned platforms, the combined diesel and gas propulsion, enhanced air defense with expanded VLS and the Type 23 air defense missile, and unprecedented levels of automation, creates a vessel that defies the traditional trade-off between capability, crew size, and cost. The integrated mast gives the Mogami a stealthy sensory advantage, letting it operate a full suite of electronics with a low probability of its own detection. Unmanned systems turn a single frigate into a system of systems and increase how much risk the Mogami can take. The Kodak propulsion system ensures both fuel economy and agility when it matters, crucial for a navy that must patrol vast sea spaces. Automation ties all of these systems together in a way that keeps personnel demands low, operational readiness high, and life cycle cost manageable. For the JMSDF, the Mogami class represents a pragmatic response to the emerging picture in naval warfare, but tailored to Japan's unique strategic environment. For export customers like Australia, these same qualities are also likely decisive.